All right. Welcome back, everybody. And we're just getting ready for the next topic, which is going to be Airyscan and multiplexing. So to kick this off, I figured the easiest thing to do would be to kind of give a little bit of theory behind the Airyscan, how it's working and why it's working the way it does. So we did a little bit of this yesterday as we were talking about hardware setup. And so I'm going to maybe skip through the first couple slides fairly quickly, but it's still a good grounding and a good place to kind of begin by thinking about why we're doing confocal in the first place, and then the losses that you get by imaging with confocal and what we can do to try to mitigate that. So if everyone can see my screen, basically the first slide to talk about this is really to step back to wide field imaging, where we're basically working with optics that are going to collect a depth of focus with a lot of background fluorescence that's out of that focal plane. And so we love working with fluorescence because it gives us very specific targets with wavelengths that we can easily separate from each other. So we can very specifically target different structures of interest. But this background haze can really limit the resolution capabilities of the systems that we're working with, no matter how good our optics are. And so confocal is one of the approaches to generate an optical slice. And by doing this, we basically raster scan pixel by pixel when we're doing laser scanning to be able to generate an image that is a thin slice through the entire tissue. And by basically stepping through Z and collecting multiple slices like this, we can recreate that same entire volume just with crisp focus everywhere and with improved resolution everywhere. And so this works great. And again, like I said yesterday, the heart of the confocal is the pinhole right here. So again, high-powered, expensive lasers and sensitive PMTs, but really having this pinhole at the same conjugate image plane as our specimen is what makes confocal work. And so we're allowing the bulk of the in-focus information to reach the detector, and we are rejecting the bulk of the out-of-focus light as well. But we're also eliminating a lot of light as we do this. And so when we think about the Airy disk, again, we covered this when we were doing pinhole with confocal yesterday. Maybe if we could always do the other one too. Yeah. Okay. So to think about the Airy disk in pinhole, what it means and how that relates to the Airyscan, it's helpful to remember that structures that are sub-resolution or single molecule, generally you're not going to see the source as it is. You're going to end up seeing a diffraction pattern just because of the optics on the system. So in X and Y, like you see on the top right, you're going to end up seeing this Airy disk pattern. And then taken together, you're going to see a point spread function in X, Y, and Z. And so this pattern basically consists of a bright central peak and then a number of concentric rings around it. And that's pretty much what we expect anytime we image. And you can see this with any kind of bead, actually, even larger beads, you'll see these rings. It's pretty cool. And then in Z, of course, the pattern is more complex and a little bit more spread out, which means that our Z resolution is always a little bit worse as well. So for structures that are in focus, that's the pattern that you're going to see. And then for structures that are out of focus, you're going to see something more like a shade of these things. So the idea is that basically the light is shifted from the central peak to the outer rings. And so, what we're doing when we're setting our pinhole to one Airy unit is we're basically, and if we take a look at that Airy pattern from the side here, what we're doing when we close our pinhole down to one Airy unit is we're basically removing those extra rings. We're only capturing the central peak. And so the Airy unit is defined as the distance to the first minima for the wavelength that we're considering here. And by doing this, we end up including the bulk of the in-focus light and rejecting the bulk of the out-of-focus light. And we do this because it's considered a reasonable compromise between sectioning and getting enough signal. So if we could close this down even further and we could get an improvement in resolution, but we really throw away light at that point. And for people doing materials research or in industry, you can maybe get away with that. But for biological samples, really, you don't have the luxury of losing that much light. Now, let's see if this movie is going to work for me. Yay. So classic area scanning mode, just to show you what this is going to look like. We are, is it going to work for me? There we go. So we're basically raster scanning the laser over the sample like we normally do for any other kind of confocal. We are oversampling. You'll notice those little rectangles, those little squares with the dashed lines are basically every pixel that we're collecting. And we are collecting signal across this entire detector. So this detector contains 32 different elements on it. The pixel in question is effectively located at the center of this. And then there is a lot of extra information that we're collecting as well. And we basically repeat this for every single pixel. And so by raster scanning across this pixel, or sorry, across the sample, we can effectively reconstruct with a little bit more sensitivity. And the reason why this works is because what we're doing with the Airyscan is we're replacing the pinhole. So in the same conjugate image plane as you would have your specimen or the pinhole, we're instead placing the Airyscan detector there. And so this detector is basically very sensitive. It's a gas detector. And where the pinhole might be 1 area unit in diameter, this is in total about 1.25 area units in diameter, but every single element is only 0.2 area units in size. And so we get to achieve the resolution that we could if we close the pinhole down to 0.2 area units, but we also get the sensitivity of collecting photons across an even larger area than we would with the pinhole setup. And so basically what we're doing is we're projecting this. Do you need to see the exam at all? Or? Okay. Oh. Got it. Sorry about that. All right. So we're projecting basically the PSF pattern across the Airyscan detector. This is obviously then a hardware solution that we're using to be able to capture this kind of resolution. But at the end, every single pixel is composed of 32 different elements of information. So we need to do some processing at the end to basically piece that all back together to a single intensity value at every position as well. And as a result of that, once we have the information from the Airyscan, we do a combination of a Shepherd sum reassignment to basically reassign photons back to where they belong in the pixel. So across the area disk or across the Airyscan detector, we basically put the photons where they belong. And then we do a Wiener filter deconvolution as well, so that in 3D, we're able to basically assign photons to the proper location in space. Both of these processes are linear, both of these are quantitative, so you can quantitate your data the same way that you would any other kind of confocal information. And I do leave behind in that literature folder as well a lot of different documents that have been generated over the years on Airyscan, including white papers and application notes and things like that. So please feel free to check those out. Some of them go into great length to describe this entire process and go into details on those different processing steps. But for the purposes here, I think we'll maybe just sort of talk about the basics at this point until you ask me for more. The results, of course, is basically a twofold improvement in resolution in every direction, in X, Y, and in Z as well. The pattern, because it's a little bit larger than the pinhole, one of the nice things about it is we're not just collecting that central peak, but we're starting to collect some of these outer orders of light information. And what this does is this gives us a little bit better ability to basically pinpoint exactly where that structure should be. So similar to applications like Palm and Storm and things like that, we actually have more information about the PSF. And again, that helps us with our localization precision in that case. It also means that we're more sensitive because we're collecting more light. So the way that we know this is that if you average with confocal, and if you need to average, let's say 4 to 8 times or so, you can generally get the same quality of image and the same signal to noise that you would end up getting just with a single scan of the Airyscan detector. And one of the nice things about it too is that we can use basically the same preparation in terms of sample as we do for regular confocal. So of course you want to be mindful of using the right cover slip, a good mounting media, all of those things, but hopefully you're doing that for confocal anyway. And so really, really powerful technique to be able to walk up to the microscope and choose to do a little spectral, a little confocal, a little Airyscan, whatever you need. I think we might skip this one for now. The other way that we can use Airyscan is to do multiplexing. And so for anyone who is on the 880, you might remember Airyscan fast. And basically by doing the calculations and by learning how to do fast, we were able to apply this kind of technique not only to the confocal when we shape the laser, but we can even just use the regular point source and we can actually figure it out that way as well. Oops, let's try that one more time. And so what we're doing in this case is because we're oversampling, our excitation beam is actually covering more than just one spot. Yeah, I think that movie might be corrupted. I can show that to you later when we get into multiplexing. I have it on the desktop for the 880 as well, so I can show it to you there, perhaps. So anyway, the excitation spot covers more than one pixel. And that means that we're actually collecting more light. And because we have this spatial detector, we can actually solve for more than one pixel at once. So we can actually solve for up to 4 this way. And I think it's going to crash again, so I'll just talk through the rest of this. The point of this is that it allows us basically to scan 4 pixels at a time. So we basically sweep across the field of view, collecting 4 pixels at once, and then we can drop down 4 pixels, speeding us up and being able to photo bleach the sample less as well, because we are not doing as much illumination as we would have otherwise. All right. The other way that we can use this is with 8Y mode as well. So your system still comes with the same kind of excitation beam shaper that we used to have with the Airyscan fast as well. And if I can get this to work, nope. All right, so I'm gonna jump over to there we go. So we can shape the beam so it's not just giving you a spot, but it's giving you that more elliptical pattern. And that allows us basically to spread the excitation out further. And then it allows you to sweep 8 pixels at a time instead of just 4. And so that mode, basically, whether we're doing super resolution sampling or whether we're doing confocal sampling, we can end up getting about an 8-fold improvement in speed as a result of that. So this method especially is very good for imaging fast samples and imaging quickly through large volumes. The Airyscan super resolution is very good for really pushing resolution and sensitivity on the system to the limit. And so the differences with these are shown here. Again, I showed this yesterday, but let's take another look. So the idea is that confocal resolution would be something on the order of 240 in X and Y and about 750 in Z. And Airyscan itself gets down to about 120 nanometers in X and Y. And about 350 nanometers in Z. So basically a 2-fold improvement in those over, let's say, your normal green light resolution. So if we're able to scan with multiplex 4Y without shaping the beam, we end up getting just a slight hit in terms of resolution, because again, we're solving this detector for more than one variable. So we end up taking a little bit of a hit on resolution, but we're still doing better than confocal would anyway. So there's a lot of power in using even the multiplex 4Y. And I know people that use it basically all the time. And it speeds you up quite a bit as well. So the other thing to take a look at here is sort of the frames per second. If you were imaging 512 by 512, let's say, confocal might be 6 frames a second. Airyscan is a little bit slower generally, and then when we start getting into the multiplex modes, you can see how much it can really speed things up. So even this 8Y mode, you can see we're still getting a decent resolution, but but we're really speeding up at that point. And that's kind of the point. So you basically have a system between the spectral imaging you can do, between the regular confocal that you can do with full spectral flexibility, and between Airyscan, between multiplexing, really addressing a large number of different experimental needs and criteria. The other thing to mention for anyone who had been working with Airyscan before is that basically the way that we're handling the data is a little bit different. There's no difference in terms of the image quality, but we're basically saving rings worth of data, and we are processing as a result much quicker. So the file size is smaller and the processing time is greatly increased. So to give you an example, you can see that here for something that might be 1024 by 1024, 150 slices. With Airyscan, that would have been basically 32 times that amount of information as would be for regular confocal, so over 40 gigabytes. And then we have basically down to 6.2 with the Airyscan 2. And likewise, the processing time is greatly increased as well. So something that might have taken about 1.5 minutes for that same volume, we can do in less than 30 seconds now. And the reason for this is, again, as I mentioned, with original Airyscan, we were keeping every single channel worth of information and saving that as the part of the raw data. And now we're basically saving instead these rings of data, which really, again, reduces that file size, with no difference in data quality in the end. Any questions so far? I'm going to, I think I'm going to just try to load up those 2 different multiplex movies before we keep going, and then we can jump right into Zen again, unless somebody has any questions to ask. All right, I believe that I have these here. All right, well, the classic one worked, so maybe let's try to skip that. These movies, of course, are also part of that literature folder as well, so you have all of these available too. Let's skip through. 2y is for the 900, so we can skip that part too. Here we go. All right. So again, we do nothing to change the excitation in this case. What we're doing is using the fact that we have the spatial detector to be able to collect more than, to be able to resolve and calculate more than 1 pixel at once. And so by doing this, we speed up about 4 times, and you can see that it takes fewer passes, fewer scans to actually collect all of that data. And if we shape the beam the way that we had with the LSM 880 on fast mode, we basically take that point source and we expand it into an elliptical profile like so. And we're able to illuminate more of these pixels as a result. And therefore, we can do up to 8 different pixels at a time, resolve those on the Airyscan detector, and speed ourselves up even further. Does that make sense? I think this is just going to be that graph that I showed you. Oh, okay. All right. Well, if there's no questions, then I will start talking about how we use it in the Zen software. And quickly, I'll remind you that, for yesterday afternoon, what we have done is to take a look at the beam path and really work with these different filters and everything to set up different configurations for fluorophore panels, for multiplex panels. And so as a reminder, the excitation side of everything is going to be exactly the same for Airyscan as it is for our standard confocal and spectral detectors. What we're doing instead is we're using these two filters, number 6 and number 9 here, to be able to trim the wavelengths down as we pass them on to the Airyscan detector. And you'll notice that, so these two filters basically in combination are what decide what wavelengths are going to reach the detector. You'll also notice that there's a couple of different zoom optics and focusing optics here. So these are something that we're going to do a quick calibration for at the very start of imaging. And you'll see that as we go through this workflow. Other than that one step, and other than the fact that we end up doing processing at the end of this, to be perfectly honest, I find these days Airyscan imaging a little bit easier even than what we had done in the past. Like, I find it, I guess, to say easier than setting up regular confocal. Are we good to go with that? It's on 20x though?
No, I switched to the 60.
Oh, you did? Okay.
Yeah,
all right. Great. How does it look?
Focus.
Okay. Do you want me to take a look quick and see?
Take a look. So it's gonna bleach so quick.
Oh, is it?
Yeah.
Okay. Maybe I'm just not gonna bother. Okay. Let's see what we have. I mean, I can always. Okay, far right will look nice. All right, I can always go to my my BPA slide too if I need to, I guess. All right, let's get rid of the stuff that we had been doing this morning. And the first step for choosing an Airyscan profile is either going to be doing smart setup or reusing a profile that you had imaged previously, or going to the experiment drop-down menu and just choosing something that says, let's say, Airyscan either SR or multiplexing. And for most of these, I have a few different combinations of lasers for doing, say, CFP and YFP instead of 488 and 561. Otherwise, the really only difference is between doing, let's say, line and frame for most of these. And if you remember from yesterday, the difference between the line and the frame is that the line scans are going to have basically our detector range wide open for every single channel. So whether it's 405, 488, 561, or 639 excitation, on the detection side, everything looks exactly the same. If we take a look at the frame one, just to very quickly review this again, you will notice that I work with a different set of filters in those two different filter wheels to be able to collect a very strict DAPI range, to be able to collect a very strict 488 range, 561 range, and 639 range, so that we can be safer in terms of our detection to make sure that we're not getting any kind of bleed through. Because with the line switch configuration, if any one of these lasers happens to excite a second fluorophore, then we're guaranteed to catch it because we have no protection on the detection side. All right, we're going to try this one first, just for kicks to see what we get. So again, I'm going to go through the workflow here effectively the same way that I had for setting up the confocal yesterday. So I've loaded a configuration, I've glanced at the setup, made sure that nobody messed it up on me. I'm happy with that. I'm going to go to my channel tab here and let me know which channels we have on it. We can try them all maybe and see what we've got first.
Definitely 647.
Okay.
Definitely DAPI.
Okay.
Maybe for 488 and 555.
Okay. I'll start then with DAPI and 647. We'll see what we got. And all right. Okay. Even the DAPI is weak, is it? Oh, there we
not
go.
weak, it's just, it's kind of gross.
And there's a lot going on with that, isn't there?
Yeah,
I mean, I might be exciting more stuff, but
yeah. Yeah,
gorgeous.
that's pretty.
All right. Okay.
Slide from August of 2019.
Wow. It's doing pretty well. Nice. So I can really back off on my laser power. That's great. Let's check out our 568 here. Something going on. Is it supposed to be those things? Maybe?
Probably not.
Okay.
I think that one
That's
was
actually not
pretty
bad.
good. Yeah,
Is this
Like,
the Tom 20?
that's the Tom 20.
All right.
Yeah.
Yeah,
So
we can
that you might be able to
work with that.
work with
There's
it.
a little bit of background, but we'll see how we do.
There's a lot of background.
Okay.
And it's kind of bleached like a,
Okay. All right. So
yeah.
I'll be gentle then. And actually what I might do is I might bump up my gain here. First thing to notice as I'm setting up the gain and the laser power is that for the Airyscan detector, we very often run it a little bit higher in terms of voltage than we do for regular confocals. So because we have the sensitivity of these 32 different detector elements, because we're doing this processing at the end, there's not as much noise. And so you'll notice that the image is not going to have the same kind of signal to noise at the same given voltage as it would for regular confocal imaging.
Oh,
And
actually, no, sorry to interrupt again. So for the Zeiss training, so they're doing so this is a super resolution called Airyscan and multiplexing at 145. I think this might be a good section that you can check if it's useful. Yeah, 1142, just 15 minutes.
just to let you know, your
not
mic is
muted.
on right now.
And
So
once you're done, yeah, but it's recording too, so we shouldn't miss much. But I think this is very nice. Yeah, because like he's just doing those live
okay.
illustrating. Yeah, so this is like a typical Zeiss confocal.
All right, here we go. So we generally run the voltage a little bit higher, often somewhere between about 8 to 850 volts. You can certainly lower it if you want to. There's no harm, and it does exactly the same thing that it would in regular confocal. You just reduce the amount of signal. You improve your signal to noise, but really, you can get away with these higher values, and you can then reduce the amount of laser that you're using. So especially for a sensitive sample like this, it can be very helpful. So I'm gonna, especially since Cassandra tells me that this green channel is gonna bleach very quickly, I'm going to bump up my gain right away, and I'm gonna work then with a much lower laser power. So that's the reason why we're going through and running this way right now. So look at that, tons of signal out. Boom, boom, boom. Let's go back. All right, let's see how we do with this. It might be a little more noisy than I like, so maybe I might just go somewhere in the middle. Let's try something like that. But you can see the laser powers that we're getting away with here are really phenomenal. The other thing that I want to mention is that you'll notice that I'm definitely not trying to fill my dynamic range on the histogram. So for Airyscan, honestly, the North American recommendation generally seems to be to keep it at about 50%. A lot of times I'll see people from Germany or people from Europe basically running it a little bit higher, but we usually try to recommend just keep it around 50% or even lower. For live samples, for sensitive samples, even running this somewhere around 20%, 30% of your dynamic range can work very well and recover fantastic amounts of signal, letting you tease out things that sometimes you can't even see by eye.
It is basically deconvolution.
There is a
It's
deconvolution
the
step.
second step,
Yeah,
right?
exactly. I mean, we couldn't do it without, the hardware and without
Right,
the
no,
setup that
I'm
we
saying
have.
the
But
post-processing
yes, there is.
is a deconvolution
There
step.
is, yeah.
Yeah.
So there's a Shepherd summary assignment, and then
Okay.
and in combination and kind of in parallel, there is a Wiener filter deconvolution. Yes. Yeah. Yeah. Yes. We're not shy about that, but it's certainly not just deconvolution with like a closed down pinhole or something like that, which is
Right, yeah. You're
really,
actually catching,
which is really suffering. Yeah.
instead of getting rid of those extra orders of information.
That's right,
You're
you're
actually
keeping them.
collecting
That's
those
right.
extra orders and using them at processing stuff.
Exactly, exactly. Plus we get the signal from the entire peak and more,
Exactly,
right?
yeah.
So
you can
for all of
reassign
those
that
reasons,
mathematically
yeah,
to
yeah, exactly. And considering the fact that the convolution is best when you have a lot of signal, like just in general, right? It's just, you know, so much easier. So so you'll notice basically that aside from those considerations, I'm doing everything the same as I had done for Confocal yesterday. So again, we can run our master gain a little higher, we can run our laser power a little lower. We don't need to worry so much about trying to catch as much dynamic range as we can, and actually we don't really want to. And from there, now that I have signal to work with, the next thing that I need to do is to, well, I should probably adjust the rest of my channels because I did bump up my voltage. And since I'm doing line switching, this voltage change is going to apply to everything. So PMT voltage is another thing that I can't change if I'm doing a line switch to go very quickly. So again, that's very much, so I can back off certainly on that power here too. Something maybe like that. It's going to be gorgeous. The red here, I'll still try collecting these anyway. Let's see what we get. But I just want you to pay attention to the laser powers that we're using here, because they're, I mean, for someone like me who has been imaging since the old days with the LSM 510, these just bring a tear to my eye. Like, it's just unreal what you can do these days. All right, so that's as low as I can go with that laser, actually. I might just leave it where it is because I don't really want to impact the rest of these.
or we could just get rid of it.
Yeah, I think that's a good idea. So one other thing here. So you'll notice that I brought up this window to do this calibration as well. And so this is one of the things that's unique to Airyscan, and you can see how easy it is to do this, right? This little window lives down at the bottom of your Zen tool window. And so if I click on this, you can see that it will bring up the window. All I need to do is to make sure that this adjust in live and continuous scans is activated. And then what it's going to do is it's going to steer this fiber using those elements that I was showing you. And it's going to make sure that that central peak is sitting right in the middle of the sample. And it's automatic. Like I just did it. It took literally seconds. And I'm done. Honestly, I can uncheck this box. I can close this down. We are finished with that calibration. So very, very simple and very fast. When do you need to do it? So you definitely don't need to do this for every single image. The idea is that it can change for different objectives, for different samples, for different cover slips and thicknesses. So the most I'd recommend that you really need to do it is sort of when you switch samples, you know, basically once for every cover slip, more or less. Or if you change objectives, for sure, you need to do it as well. So you can do Airyscan with every single one of the objectives that we have here, honestly. It's kind of a waste to do it with the 5X, but for the 25X, you get gorgeous images. For the 20X, the sensitivity that you can achieve with this is absolutely phenomenal. And even for the 10X, you can see some improvements. Now, you're not getting super resolution, of course, because these can't resolve that well anyway. But you are improving the resolution and you are getting much better sensitivity also. The thing is that if you want to sample at super res sampling, which is twice the number of pixels you would use for regular confocal, it can sometimes be take a little bit of time. So you don't normally want to use regular AirSR with, let's say, tiling experiments or something like that. That's where multiplexing comes in. Makes sense so far? The other thing I can do is I can collect a Z-stack, of course, with Airyscan, just the same as I can with anything else. But before I do that, let's actually talk about the acquisition mode here a little bit. I'm finished now with my channels. I've done my calibration. And other than the calibration, I'm still doing everything just like I would have done for regular confocal yesterday. So here, we're going to do things pretty much the same, but there's a couple things to notice. One is that we have a frame size that shows me now two different buttons here, one for confocal and one for super resolution. So if I'm trying to really push my resolution to the limit, I want to check the super res box, not the confocal box. And the only difference between these two is that this is going to double the number of pixels that I have here. That's it. Okay. And it tells you so. And you can see the sampling rate here. We now show you basically how close to Nyquist sampling you are. And so you can see that changing as well. In terms of the area, you'll notice that we're set as a default to 1.7. And if I try to go lower, number one, the number of pixels goes crazy. And it's also going to show me this little Airyscan acquisition is not configured optimally. It was doing that before anyway. But if I click on the details here, it's going to show me that my zoom is too low. And it's going to ask me, please do at least a zoom of 1.7. So this is both for processing. This is for your sanity. This is for basically just keeping everything moving quickly, more or less. And it's warning me that the Z section is wrong. That's the other reason that it was no good. So we'll talk about that one in a second. All right, so I'll go back to my 1.2 or to my 1.7. Even if I click on 1, it's going to go there. And I guess as we're talking about zoom, the other thing that I'll mention is that when you're doing Airyscan, the zoom is going to be one of the best ways that you can speed up your imaging. And the reason why I say that is because if you remember yesterday, we talked about this confocal button, and I said, I always use it for confocal. I use it in 4 steps. I hit the button, I laugh, I cry, and then I downsample. And that's how we always save time when we want to save time with confocal. In super res mode, you want to adhere to this, so I don't have the luxury of trying to downsample this the way that I would normally. And so one thing that I can do to reduce the number of pixels is just to increase my zoom. And so as I do this, because this button is blue, you can see that it keeps on adapting as I change my zoom. And so this is a great way to reduce the number of pixels and, more importantly, this overall frame time that you see right here, right? So if I'm zooming in 3 times, my frame time is about 6 seconds. If I'm doing that full 1.7, we're at about 22 seconds for a scan. So zoom is your best friend to speed things up when you're doing Airyscan. If you can zoom into something, if I don't need this empty space here, then I should just get rid of it. If I don't need the entire cell for context or the entire region for context, then if I can zoom in, it's going to make life go a lot quicker. Okay. Everything else that we're setting here is also geared towards saving time. So you'll notice that we're doing bidirectional. Again, we're just going to scan when the laser goes left to right and then right to left, so that we double our scan time in this case. We are keeping our scan speed as quick as we can. We're keeping no averaging as well. And both of these are taking advantage of the fact that we do see an improved signal to noise with the Airyscan detector in the first place, that 4 to 8-fold improvement that I mentioned. And so we're leveraging that to trade it for speed by doing this. So you can still reduce these if you want to, oops. And you can do averaging if you choose, but you don't need to with Airyscan for the most part. Everybody with me so far? Good. I'm going to go to live. I'm going to maybe just zoom in a little bit. Let's do like a nice round number, like a zoom of 2 or something like that. Save ourselves a little bit of time anyway. And let's move on to our Z-stack then. And I think I'm going to do the Z-stack bracketing the Sy4, just because it is probably the one we're going to like the most. And so let me go live. And again, either with the focus knob or using the control focus. Oh, wow. I can set my first. Again, you can work with Airyscan using the same kind of dimensionality and everything that you would for any other confocal scan. Maybe I'll go to about there, see how many that is. You can use it with Z-stack, time series, tiles, anything you want to. It's just like using another type of confocal mode. Well, that's not bad. And so I'm going to make sure, did I turn off DAPI? No, let's just turn off DAPI. And so you can see that now Zen is happy with me. I have my super resolution sampling in X and Y. I have the right zoom. I have my optimal sectioning in Z. And now it's going to tell me over here that Airyscan is optimally configured. I've done my calibrations. All I need to do is hit start experiment and we're ready to roll. We'll see how that green does.
No, let's have to process it.
Yeah, yeah.
So the slide is from OMET 2019.
Oh, is it? Okay, nice. Very cool. I was really surprised. I have my PSF beads from there too, because I came back afterwards to show somebody the CD7 like weeks later, and the box was still there. So I'm like, all right, well, I guess we don't want them.
I'm gonna make them every year anyway.
Yeah, makes sense. I'm just surprised the students didn't keep them or something. That would have been the first thing I would have latched onto. Yeah, we'll see about that green. I mean, it might be the situation exactly as you said, but it's just, I mean, there's a lot of background with it, I think. We'll see. All right, so we're almost done imaging. Does anyone have any questions about the workflow? Honestly, like I said, you don't have to think about pinhole because the Airyscan is your pinhole. Aside from paying attention to your gain, your laser power, your dynamic range, your zoom, your frame size a little bit differently, it's really no different than doing anything else. So hopefully this seems relatively intuitive and easy, and let's see what we end up getting. There we go.
I actually had a quick question regarding the bits per pixel. So I used the 880 before, and I was always taught that it should always be on the 16 bits selection. And I was wondering if that held true for the 980, or if that was just kind of like the preference of the person training me, and I didn't really know why that was the case.
Yeah, no,
you could just go into that a little bit.
Sure thing, it's a great question. So so are you talking about regular confocal mode or with Airyscan?
With Airyscan specifically.
Yeah, I mean, for regular confocal and spectral, I'd always recommend it. I mean, having the extra bit depth and, you know, working with more than 256 levels of gray and working with 65,000 levels of gray generally gives you a really nice, a nice intensity resolution when it comes to analysis. For Airyscan, I guess what I would mention is you can, and certainly now with the 980 where the file sizes are smaller, it's probably worth it. I think we generally taught to do 8 bits for Airyscan proper, just because the file sizes were so large with like 32 bits, 32 times 8 or 16-bit information at every single one of these many pixels. The file sizes just got enormous. So when you're doing, you know, just a single Z stack or a small tile or something like that, it's maybe not bad. But we had a lot of people that were using this across massive areas. And so that was one of the places where you could scale back. And anyway, by the time we do the processing, it's going to convert everything to a 16-bit grayscale anyway. So the amount of information that the amount of intensity information that the Airyscan carries across all of these different detector elements, even at 8-bit, gives you pretty phenomenal signal to noise.
Okay, great, thank you. Yeah, no, that answers it perfectly, thank you.
I feel like I totally dodged your question because I didn't give you an advice one way or the other. But again, if you're working with smaller files, I would say definitely go with 16. If you're starting to do giant experiments, this is one of the first things I would scale back on and compare the two and see. I don't think you're going to see much difference, honestly. Okay, so the last thing that we need to do, we've collected our image, that's fine, it's easy. If you try to take this image and you bring it into ImageJ or Fiji or Cell Profiler or Mars or something like that, every single one of them will spit it back at you because it doesn't know what to do with this yet. This is still a raw data file. And the reason that I know that is because underneath here, it tells me that there's a little Airyscan tab. And so this is where I can choose to either look at it as the raw confocal information, or I can choose to look at it as the super resolution version of this. And the last thing that I need to do before I'm finished and before I do any other kind of processing or analysis or anything like that is to basically process this, do Airyscan processing on this image. And so there are two ways that I can do this. So there's kind of three ways that I can do this. The first way is just with the image, go to this tab, choose whether I just want to do a single slice or the entire 3D volume or every slice as 2D, like as a separate image. So we're going to do the entire thing in 3D, and then I can just hit create processed image. And you're also going to see that there's this little auto filter here. We're going to talk about that in a second. It's set now to 7.3. Remember that number. We're going to create this processed image. You can see down at the bottom of the process, it's pretty fast. And now here is our processed image at the end. Yeah, that green background is a little rough. Let's take a look at our single channels. And the other thing that I can do is I can take this image as well, go back to my Airyscan, and I can do a sum channel here. So basically what I'm doing in this case is I'm showing this as though it were a confocal taken with a bad pinhole set to about 1.25. So not the best confocal I could take, but sort of a representation of what that would have looked like if I collected a confocal image this way. And so again, let's go back to our dimensions here. Let's make sure, okay, we've got them both. And in this case, maybe what I'll do is I'll do this, this kind of multi-view that I showed before. So I can show the wide field on one side, I can show this one. I think I'm just going to do this with the magenta for the moment. So let's turn these two off. And I can hit F11 to go full screen. And so this can kind of give you an idea of, through the focal volume here, what we were getting with confocal and what we're getting with Airyscan. Maybe the brightness on this needs to be changed a little bit. Let me check. Give it a more chance, I guess. So these were the two images we collected. And again, to be fair, what I should really do for the confocal is take a confocal image with a 1 area unit pinhole and then deconvolve that. And then that would be the more straightforward comparison. But we've done that, and there's still a significant improvement in the imaging quality at the end of the day.
Yeah, and if you look, like, can I just steal them out?
Yes, absolutely.
So like,
And
if you
there's
look
all of
at
your
this
controls on
area
here
here too, like this detail here, and you look in that same part of the, like,
Yeah,
it's
there's just
barely.
fuzz, yeah.
Yeah.
Yeah. So this is why we do Airyscan. The second way, just to finish off processing, and then like to talk a little bit more about Airyscan in general. And where are we supposed to be in terms of our schedule? Is it multiplexing already, or okay? Oh, it ends at noon. Yikes! All right. Okay, so two more things very quickly. We also have the, yeah, you're right, it ends at noon. So the other way that we could do Airyscan processing is under the processing tab. Well, actually, let me back up for a second. Let's go back to the image that we generated here. And I want to go to this information tab beside the image and scroll down to the very bottom. And you can see that for every single one of these channels, it shows me how I did the processing, and it shows me how I collected the image. It shows me the strength that it chose with that auto setting. So each one of these is a little bit different. You'll notice that the one that had a lot of background, the strength is lower. The one that had a lot more signal, better SNR, the number is higher. So what is this and what does this mean? This value that we had in our Airyscan tab right here, I set it to auto so that it could just determine where it thought the best cutoff between signal and noise is, but we can also set this manually as well. And especially if we want to be able to compare two different kinds of images or compare two different images in a series, we likely want to keep that deconvolution, the strength for everything. And so, we can manually adjust this. And what we're doing when we do so is this number represents the strength of the deconvolution that we're doing at the end. This is the negative exponent of one of the variables in there that effectively decides, what is considered noise and what is considered signal. So it's that kind of cutoff. You'll notice that when we do this in the tab here, that we really just end up getting one value for everything. We can, even if we turn it off auto, we can only adjust for one thing. If you do this formally through the processing tab, you have a little bit more flexibility and control. So if we go here, you can see that again, I can automatically choose to work with this image, my raw data. I can tell it that I want to do 3D processing. And if I turn off the auto filter here, you can see that I can actually adjust for every channel. And so if you need to do this, if your channels are very different in terms of signal quality, then you might want to adjust it here. So let's try doing something else, because I want to show you what it looks like if you push it too far. So if you decide you want to ignore the auto setting, which often people do, the recommendation I would have, I guess, is basically not to go much further than, I always like to try the auto with, I like to try the auto with a couple of different images, ones that are very low signal, ones that are higher signal, and just see what kind of values you get with it. And basically, I'll usually try not to go much more than about a 0.5 over what this one is right here. So I want to show you what it looks like if I go a full 1 or 1.5 over this, just to give you an idea of what the deconvolution artifact is always going to look like. So if I go back to my raw data here, I'm going to adjust this per channel, and we were looking at, it was anywhere from 7.3 for the green. So let's maybe do 8.5 for that one. And then these ones were 8 point something. So let's say something like 9.5, 9.5. And when you do this, the reason why you might do this is because you can really push basically the resolution even further if you can get away with this. You need enough signal to be able to do that. And so let's try these different values. I'm going to hit apply. And what you're going to see, I think, with every single one of these is sort of the classic deconvolution artifact that you will literally see on anything that you over process or over bake like this. And what that's going to look like, that green one's really hard to see. That looks pretty good. And this one looks pretty good. What that's always going to look like is basically this regularly spaced modeled appearance, or these little black pock marks everywhere. And so no matter what deconvolution you're doing anywhere, this is pretty much what it's going to look like. And so this is what you generally want to avoid. You can see that here. You can see that in the far red as well, and we can see that kind of breaking up our beautiful filaments here. Okay. So that would be the reason why I'd recommend doing this in the processing tab instead. And it's worth mentioning also that actually we can, there we go. We can batch process things as well. So if you've collected 100 images and you don't want to do them all one by one, there are a number of different processing steps that you can use that are batchable. And so for this, you can see that Airyscan is one of the things that we can do here. So I would choose this. I would add the files that I want to add for this. And I think that these were raw Airyscan, so I'm just going to pretend and pick a bunch of these if you don't mind, and you can see them here. And then the one thing that I want to point out about doing batch processing with this is that it'll look like I can shift select everything. It'll look like I can make changes to these, like maybe I don't want to do auto filter, but I want to change the value here. And it looks like I'm doing that for everything. However, you'll notice that the first one changes, but the other ones don't. So the way to work with batch processing here, this is the only catch that can drive you crazy. Make sure that you select the first one, make the changes you want, and then either copy parameters here or just right click and copy parameters. Now I can shift select everything and then paste parameters. Okay. Even better than this. So we can do batch processing like that, but the other thing that I can do is, the reason why you have an offline PC is because I can just send the images over to the other computer and have it processing while I'm still collecting. So especially when you're doing time series or large volumes or tiles or something, this can be very helpful. So the last way that we can do this is to just check the direct processing box here. And you can see that that gives me another window to open up on this computer, okay? I need to tell it that I want to add a function. And so I can go down to the processing function. I can tell it that I want to do Airyscan processing. You can see that we can also use it for decon or denoising or unsharp masking. But in this case, we want to do Airyscan processing. I can choose the settings that I want to work with. And I can decide where it's going to go. I can decide the name of it. I can decide if I want to include the name from the original version as well. So there's a lot of different parameters here you can adjust to, say, do an automatic subfolder and so forth. And at the end of it, I can decide whether or not I don't want to open the image automatically, or I do, or I want to show it side by side. So you have a couple of different options on how you see things once it's finished. And then the only thing that I need to do is I need to actually connect it to the other PC, which is the thing that you'll notice that we can't do right now. So it tells me that there's no PC connected. And this might be something that I have to set up over lunch, but let me take a look and see. I'm going to move to the offline PC, and I'm going to start ZenBlue. We're going to open it in Zendesk.
Sorry, quick question about the batch processing. Can we also have like options for the batch processing when we are choosing, for instance, for one, I didn't see the, for instance, auto cutoff for the signal and noise ratio. So could you?
Yes, sorry, they were there. I just breezed through it, I guess. So when we have our batch, we have all of our images here. So I have, oh, I see. Yeah, so you can't adjust everything per channel actually in this case. However, what you can do is if we go to single and under the Airyscan processing here, well, actually, I think it's because I have the wrong image selected. Hold on. It might be because we have an image that only has one channel. So I probably need to load it here. But either way, to get around that, if you can't just do it naturally in batch processing, which I think you can, I'm sure you can, what we can do is we can work with something like this. We can adjust it per channel. We can save that setting as a processing parameter, and then we can open that in the batch view by opening a setting here and loading it.
Thank you so much. This is very helpful.
Great. All right, so I have my offline PC open. I'm going to take a look at this right now, and I'm realizing that I might need to do a little work. Let's see. So Windows Defender is blocking our access. That's crazy. Okay, good.
Because you're trying to send it over from one computer to the other.
Yeah, that's right.
So if you, on the desktop, there should be a processing and
I was able to get it to work actually.
okay.
Yeah, but maybe we can talk about that a bit more over lunch. Anyway, I might quickly return to this after lunch because I think there's a little bit of work we need to do to finish setting this up. But basically, to do direct processing, and I might just show this to you after lunch with the camera view instead of with the screen view so that you can see both screens roughly. But on this side, on the acquisition side, you basically check the direct processing box. You tell it that you want to do Airyscan processing here. You can choose all of the parameters. And then you just need to make sure that you have the connection and you're connected. So this little link would be green and connected. And once you've got that set, you're ready to go. That's all there is to it. The other thing that I do want to talk about quickly before we break for lunch is multiplexing. And to some extent, what I'm going to tell you is that it's basically no different than what we just did for Airyscan. The workflow is exactly the same. The interface just looks slightly different. So to show you what that looks like, let me go to a similar track that I had for multiplexing. Again, just 4 colors in a line switch. The hardware layout is identical. because all we're doing is basically using and processing the Airyscan detector a little bit differently. The channel tab is only slightly different. And it's different here because, and maybe I'll just do a single channel for this so we can look at the 647. The only difference that you're really going to notice here is that your laser power shows you two different values. It shows you the raw value that you're used to working with any kind of confocal. So this is our 0.8% that's coming out of the fiber. And then we have this equivalent confocal mode. Because we are scanning less, we're calculating sort of what the effective per pixel excitation really is. And so this is maybe the number to pay attention to, but you do end up having this other value here, which is the one that we're actually changing. So I'm going to check my value on this. Let's see what we've got. You can see it's incredibly bright. This is way too much light. Maybe something like that. That's all right. Okay, so you can see that I'm doing everything generally exactly the same. Once I have a decent amount of signal, I'm going to run this calibration. I'm going to check the box to make sure I'm adjusting in live and continuous. I'm going to hit live. You can see that the detector, we're using less of the range. So we're only using 16 of those 32 detector elements to give us this sort of parallel pattern, which is what we need to collect it. But you can see, again, it's very easy to do the calibration here. And other than that, again, the biggest differences are really in the acquisition mode window. So the layout here changes a bit. You see that we've only got sort of the essentials for working with multiplex mode. And I can choose either working in 8Y mode, 4Y mode, or confocal 8Y mode. And those are those different modes that I was showing you earlier. The 4Y mode is the one that doesn't use a beam shaper, but we're still using a spot pattern of excitation. And so if I want to use that mode, I just check this one. If I want to do instead the beam shaper to do 8 pixels at once to go even faster, I can choose this one here. And you'll notice that when I do that, the frame size is going to stay the same because we're basically sampling at 2 times Nyquist for each one of these. If I want to do faster confocal quality imaging, that's what this confocal 8Y is here for. So again, the only thing that's really going to change when I do this is the number of pixels I'm collecting. And you'll see that the slider will go down to 1. And I'm collecting half the number of pixels. That's literally all it is with the interface to basically make these changes. So it's the same concept, it's the same style as we did with Airyscan, and the processing at the end is going to be the same as well. It's just a different interface. So if I wanted to, I could go somewhere in the middle. If I want to go quicker, if I want to get better resolution than confocal, but I want to go quicker than this, then I can just manually drag this slider somewhere in the middle. And again, all that's doing is basically changing the number of pixels that I'm collecting. So let me show you maybe what the 4Y is going to look like. I'm going to do a Z stack again, and I'll set my first and last quickly. We'll just do a single track. And let's see how quick this acquisition is compared to, I'm doing 0.3 zoom here. So let me zoom in and we'll do 2 zoom to make it match the Airyscan image that we had collected earlier. And I think we had gone to about here, set my last, come down here, set my first, make sure that we have the optimal interval. It's about the same number of slices in this case. It's only a single channel, I guess, so that's where we're kind of cheating a bit. But if I start the experiment here, then we'll see how long this is going to take. And if you were in the room, and maybe through the microphone you can hear it, that the Z piezo just started and it never stopped. And especially for multiplexing, this is where we want that piezo to be activated. So you saw how quick that was. Again, we can go to Airyscan, we can quickly do our 3D acquisition, get that process data. And we can take a look at these and compare them side by side and everything. I'm not going to take the time to do that right now because we don't have a lot of time, but you can see the quality again is very nice. Let me switch now to the SR8Y mode, and I'm going to show you basically the same kind of thing. So we're now doing, you can see that the speed also includes another metric here, which is just how many frames a second. So we don't even care about dwell time anymore. We care about how fast we're going. So 4Y was 7 frames a second. This would be 16 frames a second. Confocal 8Y would be actually still 16 frames a second. That doesn't make sense. There we go. 33 frames a second. So let's do this one. This one's fun. We'll start that experiment. We're done. Yeah. This is where, yeah, exactly. So this is unprocessed, right? So let me process this quickly. And this is an important point too, is we are taking a hit on resolution here, of course, right? So you are starting to make trade-offs as you're moving to these different modes. Again, we can take a look at this relative to confocal, but this should be better. It's not fantastic, honestly. Let's take a look at the Sy4 mode and we'll see what that ends up looking like. So we can start this experiment and try that. Again, the speed that these are being acquired is really just outstanding. And that's the point of these. So let's try this, let's try 3D. So one thing that I will say is that using these techniques, this is sometimes where I do start to play with my dwell time a little bit. I usually don't average, but I will start to play with my dwell time a little bit just to try to improve the amount of light that we're getting, because we are going so fast that we're just leaving photons behind. And so if we take a look through here, the SR8Y mode generally looks really pretty nice, but especially for the confocal 8Y mode, this is where we're starting to make some trade-offs, right? This is your choice and why it is such a flexible system. You can push it to do speed. And just to give you an idea of what that speed looked like, again, let me actually do a time series where we are just going to do, let's say, 100 cycles with no interval at all. And so if I start that experiment, this time doing the confocal 8Y mode, if we set it to gallery mode here, I mean, this is why we use it, right? It's just exceptionally fast. But of course, we're taking a hit on the quality, especially compared to SR mode. Now, if you can tweak your sampling a little, or tweak your scan speed a little bit so that you're getting, something close to confocal resolution, then awesome. But I do find that you need to play with that a little bit to get it to match. But tons of data very fast. If you are working with fast things, then you can move lickety-split. And if this quality is all you need for like a giant volume to be able to say something about that, then that's a good reason to use it as well. Personally, what I find, I mean, out of all of the different modes that are available in the system, I can tell you that my favorite is the SR4Y mode. You don't really take much of a hit in terms of resolution compared to Airyscan. There's almost no reason not to use it. SR8Y mode, it's decent as well, but I mean, this is just my favorite. I will use this for almost everything. And then if I have to, I'll dip down into these or push to Airyscan when I'm really trying to push the limits of something. Okay. Okay. So there was a question on whether I can show you to change the range of the emission with this filter. Yes, you can. So this was something that we spent a little time with yesterday. And this was where I had showed that basically you have two different filters underneath the little emission curve cartoon. The first one here that says plate at the moment, this one, if we take a look at the scan head again, that is this filter right here, number 6. So this is the one that chooses whether things go to the confocal or through to the Airyscan detector. And so that's the reason why we have, first of all, a mirror. This would be confocal. Plate is everything goes to the Airyscan. And then there's a couple of different short and long pass filter options here as well. And then beyond this, So let's pretend for Sy5. Let's see. Let's go do this for another one. Let's go do this for the green. So let's say for green, for example, that I want to do something like a long pass 525. Not a good idea, not the best choice. Maybe I'll pick something else. Maybe I'll pick the long pass 460 or the short pass 615. So short pass 615 would make sure that I don't collect any red if I happen to be cross-exciting it. And you have also a second filter option down here. And this filter option, if we take a look back at that scan head, is the second filter wheel that we have over here, number 9. So this is going to further trim the detection range that the Airyscan catches. And so the combination, the sum total of number 6 here and number 9 is going to determine the wavelengths that go to your detector. And so we can make crude choices here, and then we can make different multi-pass filter choices here. So if I wanted to, I could trim this down even further with something that looks appropriate like this, 495 to 550. And you can see that this might be a good choice to get green and cherry, but if I have some Sy3 here or some orange, this might actually catch it as well. So maybe instead I want to choose something like this one to only catch this range. And honestly, if I'm going to do that, I really don't even need to bother with this one. So I could put this back to a plate and we're still doing the same thing. Does that make sense and answer the question?
Yes, thank you.
Okay, great. Does anyone else have any other questions? I guess the advice that I would have is just really, you have the system with all these great tools. When you come here with the sample in the first place, try a few of these different modes and see what you like. Just like working with laser power and gain, just like working with averaging and dwell time and stuff like that, you might as well give each one of these modes a shot, because you might find something that works really, really well for your sample, for your application, and gives you much faster acquisition as a result.
Okay, so
Okay.
if there are no other questions, we'll shut down for lunch and then we'll reconvene at 1 o'clock.
Yep. So 1 o'clock, we'll do a little direct processing just to cap that off, and then we will dive into carriers, I guess. Okay. Thanks, everyone.